Okay, let's consider what happens to an AVL tree and how it balances itself. So let's take a look at the tree on the left. This is our original tree, and we will do both insertions, an insertion example and a deletion example, so that we can see how that works. So first of all, let's calculate the balance, the factors in each of these, so that we convince ourselves that we've got a tree that is in balance before we add or take away anything. So this is 0, 0, 0, 0 here and here. And this is 0, 0, and this is 0, 0. Left child has height 1, right child has height 0. Left child has height 1, right child has height 0. Left child has height 1, and the right child has height 2. Here, the left child has height 0, and the right child has height 1. Here we've got a 2 and 3. And then here we've got 2 of the height of the left child and 1 height of the right child. And finally, we've got 4 and 3 at the root. So as we look at this situation, we will determine that there are no deltas that are greater than 1. And so the tree is considered in balance. So let's take a look at what happens with respect to the balance function once we insert a node into this particular tree. Okay, so I'm going to insert the node in green so that we can see what happens. So I'm basically going to insert the node right here. And you will remember that when we insert the node, the balance function is immediately called. So we've inserted the node here, and the balance function is called, and we assess the heights of these two trees, and they're 0. Now, this is not going to update the entire tree, because how did we get to this node? Well, we got to this node because it was less than this particular node. Okay, so the recursion will unwind, i.e. we will backtrack to this position. And in this position, we have now a left subtree of height 1 and a right subtree of height 0. We are still within balance, so we have nothing to do. And then the recursion unwinds to this point. When we get to this point, we will notice that we have an imbalance situation. Okay, and so this is going to require that we fix it, and the fix takes place at this point. Okay, if you'll remember the balance function, it invokes the fix at this. It invokes the rotation functions at the time that it determines there is an imbalance. So let's do what we did previously, and that's let's circle our node that is out of balance in red. And so it's this node. This is the node that's out of balance. And this is an outer situation. It's out of balance because the left child of its left child is longer than the right child. So it's left heavy, and that left heaviness happened in the left subtree and not in the right subtree. Okay, so this is a single rotation. Now remember, we're at this node, and we're rotating this particular node with its heavy child. And so what does this look like? Let's redraw the tree. So we're going to redraw the tree. Next to it here, we've got Okay, we'll come back to this tree in a second because that's the tree we rotated. And so when we execute this particular rotation, I'm going to keep the node that was originally here. Okay, so that node is now this one. The node I just drew, this node is now this node, which I rotated into the position. And let me draw the node that was in green. And finally, the node that was already in blue and was the out of balance node. Right? And we're going to give it a little bit of shade of red so that we remember that it was the one out of balance. Okay, so this is the picture after the fact. And notice that you'll recall then that the function, the balance function, was invoked from this particular node, and that is still where we are. Okay, so the recalculation then ends up here, and we now have a 1, 1. And then the recursion will unwind to this point, and we now have a 1, 2. And then this was called from here, so it unwinds to this point, and we now have a 2 and 3. And this unwinds to this point, and we've got a 4 and 3. I'm leaving those other heights unmodified because these are the only heights that get modified in this particular, after this insertion. And so nothing else changes in the tree, and the tree is basically back in balance. Now let's take a look at a deletion. Okay, so we have the same tree that's over on the left, the same tree that is here is what's depicted here, and we're going to delete a particular node. So we want to delete, and notice I placed delete in quotes because you'll remember that we actually delete by substitution or by copying. And so we're deleting this particular node, but really what happens is that we will end up deleting this node. As I consider this particular node and I look at its right subtree, the leftmost node in the right subtree, which is what I'm going to substitute in its place, is this node. So this is the one we're actually deleting. So what we're going to do is take the value that's in this node, and I'm putting a dashed line here, and I'm going to try to write value here on the side. We're copying the value from this node, which is the node that's actually going to be removed, and placing it into the quote-unquote node being deleted, right? Which is really this node. This is the node we're trying to get rid of. And so when we do that, this particular node will be deleted. Okay, so I'm going to show that. And then we will recalculate the balance factors. Okay, so this node, I've copied its value, so it's no longer needed. And I'm going to make that X. And now let's recalculate the balance factors. In this particular case, this node now has height 0 and height 2 in this case. So it is the out of balance node. It is the out of balance node. And the out of balance condition is where? The out of balance condition is in the left child of its right child. This is an inner case and will require 2 rotations. Okay, and so I'm going to call this particular one here. I'm going to call this P. I'm going to call this Q, and I'm going to call this one R. So here's our first rotation, yielding a tree that looks like this. Okay. The second rotation then, so let me relabel these. So this is still P here, but we rotated Q and R. So R is now here and Q is here. The second and we're now in an outer case, correct? So the second rotation is this rotation. And that gives us the following tree, which I will draw down here. And now P is here, R is here, and Q is here. And if we recalculate, we'll realize that we're now back in balance. So we've got the node out of balance was P. Okay, so that's a 0, 0, 0, 0. This is a 1, 1, and this is now a 2, 2, and this is now a 3, 3. Okay, so we unwind the recursion all the way back to the root, and the situation is fixed. And so the bottom line in all of this is that Rebalancing will automatically take place at the lowest level. You don't have to force that. It automatically takes place at the lowest level, and it fixes any problems with imbalance above it.